Hello students, I'm Anil Sunam and I'm your physics guide. So together we'll learn different topics of physics. And you see, physics is a very interesting subject. But it becomes more interesting when you actually understand the concepts behind the different topics. So here, I will be focusing more on the concepts. So once the concept is clear to you, it will be very easy for you to understand the topic. So here we go. In this particular session, we will take work. All right? We'll take the chapter on work. In our day-to-day life, we do so many physical and mental works like running, walking, washing clothes, washing utensils, reading, writing, and eating also, and lots of other things also. So we consider all these things as work. But in physics, the concept of work is something different. So that is what we are going to understand. Okay? So let us take this toy car, okay, which is at rest. Now in order to move it, you know what we have to do? We have to apply external force. So here we go. So I'm applying force to the toy car in order to move it. Now let's start. 1, 2, and 3. Now the car moves. Okay, stop it here. Now you see the car has traveled some distance, isn't it? That means there is a displacement produced. So in this case, okay, according to physics, some work is done. So we actually applied force in this case, isn't it? And that applied force produced the displacement. So whenever a force applied produces displacement, we say some work is done. So then how do you define work? Work is said to be done when the point of application of force moves and is measured by the product of force and displacement. That is, work is given by the product of force and displacement. Let's now take few more examples of work done. Okay, lifting a bag, that is also work done, because in this case you will be applying force and there will be displacement of the bag. So lifting a bag is an example of work done. Next is kicking a football. So when you kick a football, you apply force, isn't it? Because of which the football gets displaced. So there will be displacement produced. So we say some work is done in that case also. And similarly, so hitting a cricket ball with a bat, that is also some work is done in that case. Okay? So you see, in all these cases, for work to be done, there are two things which are needed. Okay? One is the force and the second one is the displacement. Okay? So when there is force applied and that if that force applied produces displacement, then only we say some work is done. Okay? Now in order to understand that, let me take this example. Now I'm going to push this wall. So am I applying force? Yes, I'm applying force, isn't it? But is the wall moving? No, it's not moving. So what is the displacement produced here? 0. There is no displacement. So when there is no displacement, the work done will be 0. Okay, so the work done depends on two things: force applied and the displacement produced. So according to definition, work is equal to the product of force and the displacement. All right. Let's now calculate the work done in different cases. All right. Now in the first case, you see there's a car, and let's say a force of 2 unit is applied to the car, due to which the car gets displaced. And let's say the displacement produced in this case is 5 unit. So according to the definition of work done, work is equal to force into displacement, and work is equals to force is 2 unit, displacement is 5 unit, and hence the work done in this case is 10 units. Now let's take another case. Okay, now I'm taking the same toy car, but in this case I will not apply the force horizontally in the direction of the displacement. Okay, so let's say the toy car is pulled with the help of a thread inclined at certain angle with the ground. So let that angle be theta. Now in that case, the force applied and the displacement are not in the same direction. So in that case, you need to have a little bit of knowledge of trigonometry. So here I will not go into detail of trigonometry, but whatever we need here, okay, that I'll let you know. Let's say this is a right-angled triangle ABC, where angle B is a right angle, and you must be knowing that this vertical line at the vertical side is called the perpendicular. The lower one is called the base, and this oblique side is called the hypotenuse. Right? And let's say the angle here is theta. So this theta can have any value. It can be 0, it can be 10, 20, 80, 90, whatever it is. All right? So theta is just an angle. Okay? Now, when we take any two sides, the ratio will have a name. Don't get confused, all right? So, we have 3 sides, perpendicular, base, and hypotenuse. Okay? So, out of the 3 sides, I'll take any 2 sides. Okay? So, I'm taking the base. Okay? And the hypotenuse. Okay, base and hypotenuse. So the ratio of base and hypotenuse is called cosine theta. Cosine theta. So it may be new for you, but it's not so difficult for you to understand. Okay, so the ratio of base and hypotenuse is called cosine, and in short we write cos only. It's called cos theta. Okay, in short we write cos theta. So base by hypotenuse is cos theta. So since we require the concept of cos theta, okay, this is the meaning of cos theta. So cos theta means the ratio of base and hypotenuse. Right? Now look at this chalk. When I apply force, the chalk breaks into 2 parts, isn't it? Similarly, any vector quantity, okay, let's say this line represents vector P, Okay, so vector means it can be force, it can be displacement, it can be your weight also. Weight is also a vector quantity, isn't it? So this is not only force, but this is any vector. Okay, like a chalk can be broken into two pieces. Similarly, a vector can also be broken or split up into two parts. Okay, a single vector can be split up into two parts. Actually, this is in your class 11 syllabus, but since you require a little bit of this to understand another type of work done, so let's try this one also. Okay, now when we break this force into two perpendicular components, not any other components. Okay, what kind of components? Perpendicular. That means you can imagine this to be x-axis and you can imagine this to be y-axis. Okay, let's say this is the origin, this is the x-axis, this is the y-axis. So one component है यो p को एउटा भाग चाहिँ योपट्टि हुन्छ अनि p को अर्को भाग चाहिँ यहाँ. जस्तै त्यो अघिको एउटा सिंगल चकको दुईटा पिसेस थियो थिएन है, त्यस्तै यो वेक्टर को दुईटा पिसेसहरु चाहिँ एउटा यहाँ छ, एउटा चाहिँ यहाँ छ. अलिअलि बुझिँदैछ नि यो? Now for that we drop a perpendicular here. Similarly from here we drop a perpendicular here. Alright? Now यो जुन चाहिँ छ नि यसलाई नाम लेखे मैले m अनि यसलाई के लेख्दैछु n. So this OM represents one part of the vector and ON represents another part of the vector. Alright? Now, अब कुरा आयो, what is the value of this and what is the value of this? So, if this angle is theta, अघिको याद आउँदैछ नि यो? If this angle is theta, the component out here, okay, p को भाग यहाँ है, the component of p along this direction will be now p cos theta. And similarly here, the component of p will be p sin theta. And sin theta means the ratio of perpendicular and hypotenuse. Okay, so the ratio of perpendicular to hypotenuse is sin theta, and the ratio of base and hypotenuse is cos theta. So whenever you split up a vector into two perpendicular components, okay, their values will be p cos theta and p sin theta if this vector is p. Okay, if this is r, it will be r cos theta, r sin theta, like that. Alright, so one will be p cos theta, the other one will be p sin theta. Now let's come back to that case where a toy car is pulled by a string in this direction and the car moves in this direction. That means the force and the displacement are not in the same direction. So in that case, what we do, you know, this force is a vector quantity and this can be split up into two perpendicular components, cos and sine component, isn't it? So then use the previous concept and tell me what, and think that what should be the component of p along this direction where you have angle. What is that? The component of p along this direction will be p cos theta, isn't it? So now work done in this case is force. That means force in this direction is p cos theta into, which is the displacement, s is the displacement. Therefore we get the formula force into displacement into cos theta. So this is a general formula for work done which can be applied in any case. Okay? Let's now take the topic on types of work done. Now according to the direction of displacement and force, okay, work can be divided into 3 categories. Okay, so first of all, let's take this example of that toy car. So when you push the car moves some distance till you apply the force, isn't it? So here the force applied is from left to right, and the displacement is produced in the same direction, isn't it? So in such a case, when the force and the displacement are in the same direction, okay, the work is said to be done by force. Okay, so since force and the displacement are in the same direction, the angle between force and the displacement, they are in the same direction. So here the angle between the two is 0 degree. No? So when theta is 0 degree, work done will be, so I am using that formula of work done, that is force into displacement into cos theta, and theta in this case is 0 degree. P into S. Now cos 0 degree is 1. The value of cos 0 degree is 1. So this is it. So this is the work done, and you can see it is positive. So work in this case is positive, and this work is known as work done by force. Then what is work done by force? Work is said to be done by force when the displacement is produced in the direction of the force. You all know every object is pulled by the earth towards its center. That means when I let this chalk, okay, it will drop by itself. Okay, that means the gravitational force of the earth will pull the chalk vertically downward. Again, I'm taking the same example of this toy car. So when we lift it, the car gets lifted by some distance, isn't it? So in this case, displacement produced is in vertical direction, but the gravitational force is directed vertically downward, isn't it? So they are oppositely directed. So in this case, the work is done against the force of gravity, isn't it? Such kind of work is known as work done against force. So how do you define work done against force? It is work is said to be done against force if the displacement is produced against the force. Now, to see whether it is positive or negative, we do like this. What is the angle between the displacement and the force here? It's 180 degrees. So work done is P into S into cos theta, and the value of that theta is 180 degree. PS is PS. Now the value of cos 0 degree was 1, no? The value of cos 180 degree is minus 1. So when you multiply this, PS into 1 is PS, and plus into minus is minus. So the work done in this case is negative. Okay, so the work done against force is also called negative work done. Let's now take the case of a man carrying a load on his head and moving horizontally. Now in that case, what is the force acted? The gravitational force acting on the load is directed vertically downward. And where is the displacement produced? It's horizontally, isn't it? The displacement is produced horizontally. So what is the angle between the force and the displacement out there? It is 90 degree, isn't it? So let's find out the work done in this case. Okay, so in this case, force and displacement are perpendicular to each other. Formula, as you know, is this, and the value of theta is 90. Now you have to remember, okay, so cos 90 degree is 0. So 0 into any number is 0. So what is the work done here? 0. So there is no work done. So this is the case where there is force, there is displacement also, but still the work done is 0. There is no work done. Okay, so this is the third type of work. So in this case, you see this formula, work is equal to P into A sin cos theta, can be applied to find out the work done in any case.